amplitude modulation. When that is the modulation technique used at the transmitter side, how do I do the detection symbol by symbol at the receiver side with controlled inter-symbol interference? And another one is M level PIM. Okay. Just to have what I discussed in the previous class. So I was discussing about the design of band limited signals with controlled symbol interference, that we call it as partial response signals. Okay. So as I said, to meet the Nyquist criteria for zero inter-symbol interference, okay. So I told about the raised cosine role of filter and about three cases: when f is greater than 2w, when f is equal to 2w, when f is less than 2w. Right? What happens? Then so this is one pulse, okay, signal pulse, which we will be able to realize physically the transmitting and receiving filters. That pulse is known as the duobinary signal pulse. Okay, duobinary signal pulse. So how do we define the duobinary signal pulse? So x of nt will be equal to 1 when n equal to 0 and 1, and it is 0 for other values of n. So this is how the pulse looks like in the time domain. Okay, as I said, when f equal to 2w, we use the sinc function. Only one pulse exists, but which is not physically realizable. So that is why we are going for adding one more pulse, that is at n equal to 1, that we call as controlled inter-symbol interference, right? And so in frequency domain, this is the expression, and so I can express this x of t as, see, this is one sinc function, sinc of 2wt plus sinc of 2wt minus 1, right? So from 0 to t, that is from minus t to t is one sinc function. Then another one I'm having at t also at t is equal to capital T is also I have a pulse, which amplitude is 1, right? Another pulse, so that I can write a shifted version of this. That is a sinc of 2wt minus 1. So this pulse we call it as a duobinary signal pulse, and the frequency response of this pulse, duobinary signal pulse, looks like this. Okay. So what we observe from this frequency response of this duobinary signal pulse is there is a smooth transition. Okay, means the spectrum of the signal x of t decays smoothly to 0, so which we will be able to realize physically. This is what I discussed in the previous class. The next version of this is modified duobinary signal pulse, right? So what I said in the modified duobinary signal pulse is I am defining x of nt as 3 values. So when n is equal to minus 1, I have a one sinc function. Its amplitude is 1, this one. Then when n equal to 1, also I have another sinc function. Its magnitude is minus 1. Okay, this is what the modified duobinary signal pulse. This is another version of the duobinary signal pulse, where I can achieve still better relation of the transmitting and receiving filter. So the corresponding means I can express this x of t like this. Means there is one sinc function, x of t is equal to sinc of t plus capital T by t minus sinc of t minus capital T by t. Right? This is for t plus sinc of t plus capital T by t, and this is for minus sinc of small t minus capital T by t. Right? So its frequency domain expression will be like this, because sinc function we write as sin pi x by pi x, right? So that will be written as what? E power j theta minus e power minus j theta by 2j. In that form I have written, and by simplification I will be getting this. So the frequency response of this modified duobinary signal pulse will be looking like this. So here what I am finding is this spectrum, means the spectrum of the signal at f equal to 0 is 0. So that makes gives me the flexibility in designing a transmitting and receiving filter which will not pass the DC signal, right? So that's what I discussed about those two things in the previous class. In general, we write the partial response signals as this, yes, x of t as summation of n is equal to from minus to infinity x of n by 2w sine of this by sine of 2 pi w of t minus n by 2w divided by 2 pi w of t minus n by 2w. And its spectrum will be written like this. I said that these signals, okay, allow us to transmit information symbols at the rate of what? Nyquist rate, that is 2w symbols per second. So this is what I discussed in the previous class. Okay, so today, as I said, we'll discuss about the symbol by symbol detection. Okay, symbol by symbol detection at the receiver side, right? So actually, for a detection of the data with the controlled intersymbol interference, okay, there are two methods. Okay, one is the symbol by symbol detection method, and another one is maximum likelihood criteria for detecting the sequence of symbols. Okay, out of these two methods, the first method, that is a symbol by symbol detection method, is is relatively easy to implement. Okay, but this maximum likelihood criteria for detecting the sequence of symbols will minimize the probability of error, but it is slightly little complex to implement. Okay, so we treat these two methods, okay, based on the PAM signal. Okay, means we consider two cases, as I said. One is binary PAM, another one is multi-level PAM. Okay, so I hope you are with me. Hello. Hello.
Yes, sir.
Mm. So shall I proceed? Okay, so let me consider the spectral characteristics, that is x of f. Okay, for the partial response signal, right? That is split between transmitting and receiving filter. So I know this is the GT of f is the what? Impulse response of the transmitting filter, and GR of f is the impulse response of the receiving filter. Right, GT of f is what? Impulse response of the transmitting filter. GR of f is the impulse response of the receiving filter. And this x of f, what I am saying, is the output of the receiving filter, right? So that will be what? Square root of this one. GT of f is equal to GR of f is equal to square root of x of f. Okay, square root we are taking. So let me consider the binary signal. Already I defined. How do we define binary signal? So x of n will be equal to 1 for the value of n equal to 0 and 1. For other values of n, it will be 0. Right? So I will be writing these samples at the output of the receiving filter in this form. So this is the output of the receiving filter. So I denote that as ym, okay, y suffix m, which is equal to bm plus wm. Okay, and this bm can be written as am plus am minus 1. So am is the what? Transmitted sequence of amplitudes. As I said, if I consider the binary, I'll tell you what it is, right? So AM is the present pulse, and AM minus 1 is the previous pulse. Okay, so present and previous is the what? Controlled ISI, right? So that is what I am writing. BM is replaced by AM plus AM minus 1. And this is the noise sequence. Omega M or WM is the noise sequence, right? So let me consider the binary case. So in that case, I am considering the transmitted sequence of the amplitudes, that is AM, as plus or minus 1. Means plus 1 for binary information 1 and minus 1 for binary information 0. Okay, so with that, this value BM will take these values minus 2, 0, and 2. Right? And the probabilities are with this is 1 by 4 and this is 50% and this is 1 by 4. Okay, with I am considering these are the probabilities of occurrence of these symbols. Okay, so I said AM and AM minus 1, right? AM is the present pulse and AM minus 1 is the previous pulse, right? That is what I receive at the output of the receiver, right? With the additive Gaussian sequence. If I consider, let's say, if I want to detect the AM minus 1, Okay, AM minus 1 is the what? Detected symbol from M minus 1 signaling interval. Right. So its effect on BM, right? That is the received signal in the M signaling interval can be eliminated by subtraction. Means present and previous pulse, that is known as the intersymbol interference, right? They overlap each other. Their duration will be overlapping each other. So that we call as intersymbol interference, right? So I will be able to remove the effect of AM minus 1 on AM, right, while detecting BM by doing subtraction. Okay, I can eliminate that by doing subtraction, right? So that allows me to detect the AM signal, means the present symbol. And this process can be repeated sequentially for every received symbol. So while doing so, what happens? There will be propagation of the error. Okay, so how does that error propagates, right? So let me see that. See, if the detector makes an error in detecting the AM minus 1 pulse, right, and its effect will be there on BM, right? Its effect on BM is not eliminated because it is reinforced by the incorrect subtraction, right? If there is any error in that detection of the AM minus 1, because it will have effect on the AM. So when there is error effect on AM, that leads to again detection of the AM also leads to error, right? So to eliminate this error propagation, we use the pre-coding. Okay, we use the technique called pre-coding, right? So what is that pre-coding is? So we do the pre-coding on the data or the transmitter. Okay, instead of eliminating the controlled intersymbol interference by subtraction at the receiver. So what I was telling in the previous sentence is we are doing subtraction, right? We are doing subtraction for detecting AM minus 1, right, from AM, right? So to that leads to error propagation. To avoid that, what we do the pre-coding on the data at the transmitter instead of doing that eliminating the controlled intersymbol interference by subtraction at the receiver. Okay, so you will be able to understand this concept clearly with the example. I have example in the next slide. Let me say that. So just I am telling and giving you the mathematical equations here. So that pre-coded decoding, right, is performed on the binary data sequence prior to modulation. So before modulation, the pre-coding will be done. So how do we do the pre-coding? This is the formula for that. Okay, the input data sequence I denoted by DN and the pre-coded sequence I denoted by PN. Okay, so I'm taking here PM is the pre-coded sequence that will be equal to DM is what input data sequence. So this is what modulo 2 subtraction and PM minus 1. See, PM is present and PM minus 1 the previous one, right? So I am doing the for pre-coded. How do I pre-code a sequence? The present sequence will be equal to the modulo 2 subtraction of the present input data sequence and the previous coded sequence. Okay, for different values of M, right? So let me take the example. Let me go through the equations, then I will do the example. Okay. I hope this is clear. The pre-coded sequence, what do we do? PM is equal to DM is the data sequence. This is a modulo 2 subtraction, modulo 2 subtraction and as well as modulo 2 addition are same, right? And this is the previous decoded sequence. Okay. So for binary, as I said, let AM will be equal to -1 if I consider PM equal to 0. That means the present pre-coded sequence is 0. For that time, AM is equal to -1. AM is our transmitted sequence pulse. Now, -1 means it is, I denote binary information 0, right? So, I consider the pre-coded sequence value will be 0 and AM will be equal to 1 if PM equal to 1. So, with that, what I can write is the value of AM, okay, will be equal to 2 PM minus 1. Okay, so let me consider first the without the effect of noise on the receiver side. Okay, I'm assuming that the additive weight Gaussian axis is 0. Okay, without the effect of noise, what will be the output of the receiving filter? So that I can write it as Bm is equal to, already I wrote this equation, right? Am plus Am minus 1 plus noise I used to write, right? In the, I think in this slide, Ym is equal to Bm plus noise. Right? I said Bm is what? Am plus Am minus 1. And so I'm considering this noise is 0. Okay, in this case. So with that, I'm writing Bm as Am plus Am minus 1. But already I said Am is what? 2 Pm minus 1. Okay. So I'm just substituting the value of that here. Am as 2 Pm minus 1 plus Am minus 1 as 2 Pm minus 1 minus 1. So I am just rearranging that. So I'm taking 2 outside and writing Pm plus Pm minus 1 and then minus 1. Right. And again, I can rearrange this now. So Pm plus Pm minus 1 will be equal to what? Means this 2 will come this side, right? So 1 by 2 into Bm plus 1 I will get, right? So this data sequence, right, will be is equal to what? Pm XOR with Pm minus 1. Okay. Means I'm doing the XOR operation. The data sequence, input data sequence will be equal to Pm XOR with Pm minus 1. Means present and previous. Right, I'm doing the XOR operation. So it follows that the data sequence DM is obtained from the BM using this relation. What is that relation? So DM is equal to 1 by 2 BM plus 1. So this is the mod 2 operation. Okay. So here I will be considering BM. The value of BM will be equal to plus or minus 2. Means if I consider the value of BM as plus or minus 2, then what happens? If it is plus 2, so 2 by 2 is 1, 1 plus 1. Means XOR operation, no? 1 XOR with 1 will be 0, I get, right? So then DM will be equal to 0. And if I consider BM as 0, then the value of DM will be equal to 1. Okay, I hope this is clear. These equations. Hello?
Yes, sir.
Yeah.
Yes, sir.
If you have any difficulty or doubts, you can ask. You can always stop me, okay, in between. Yeah, let me consider this example. I think all of you can note down this example. So take this binary data sequence DN as what, triple one, 1 1 1, then 0 1 double 0 1 triple 0, then double 1 0 1. Okay, this is my input data sequence. I repeat once again: 1 1 1 0 1 0 0 1 0 0 0 1 1 0 1. Okay, this is my input data sequence, and this is binary. Okay, so we need to determine the pre-coded sequence, that is denoted as PN, then the transmitted sequence denoted as AN, then the received sequence BN, and the decoded sequence DN. Okay, so how many things we are supposed to find out? See, PN, that is a pre-coded sequence, transmitted sequence AN, then the received sequence BN, then the decoded sequence DN. See here and there written, see, transmitted sequence I wrote there A suffix M. Here I am writing A suffix N. So don't confuse with that suffix, okay? Similarly, the decoded sequence also D suffix M, and here I have taken as D suffix N. Similarly, the output of the received sequence B suffix M. So it is B suffix N. So don't be confused with this notation, okay? So all formulas, everything remains same. And even taken from the reference, right? So here I have written data sequence. It should be small d, okay, small d suffix n. So first I wrote the data sequence, okay. Please carefully understand this. It is very, very, very simple, and it will be asked in exam. Okay, there will be a definite pakka question on this topic. That too, they will ask this example only. Okay, for 6 marks or 8 marks, they will ask you to find out these things. Okay, so first you write the data sequence, then the pre-coded sequence, no, that I denoted as PM. They said it is PN, right? P suffix N. So here I am considering first the initial bit as 0. Okay, initial bit as 0. Then how do I find the pre-coded sequence? It is what? XOR of the present data sequence and the previous PM, right? I hope you are familiar with that equation, no? Yeah, PM, right? DM, this is the modular to subtraction, right? PM minus 1, right? Yes or
Yes,
no?
sir.
I think, yeah, it is there. Okay, yeah. So what I do, so XOR of these two will give you this value. So 0 XOR with 1 is what? 1. I'm getting this as next precoded sequence, right? Then XOR of these two, XOR of the 1 XOR with 1, I will be getting 0, right? This is my next bit. That is the precoded sequence. Then the XOR of 0, 1 is what? 1, right? I will be getting this bit, right? Like that, it continues. I hope you will be able to understand. You can do it by yourself. When you do it, I have taken here the initial reference bit as 0. Okay, I am XORing these two. 0 XOR with 1, I am getting 1 as the pre-coded sequence for this. Okay, then 1 XOR with 1, I will be getting 0. Right? This is the value of PM. Then 0 XOR with 1 is 1. Then 1 XOR with 0, it is 1. Right? Then 1 XOR with 1, it is 0. Right? 0 XOR with 0, it is 0. 0 XOR with 0, it is 0. 0 XOR with 1, it is 1. 1 XOR with 0, it is 1. 1 XOR with 0, it is 1. 1 XOR with 0, it is 1. Right? 1 XOR with 1, it is 1. 0 XOR with 1, it is 1. 1 XOR with 0, it is 1. 1 XOR with 1, it is 0. Right? So all are fine. Then how do you find the transmitted sequence? So here again, don't be confused with this symbol. It is A suffix n. Okay, here it is the I suffix n. You take it as A suffix n. That is the. So I told about this pre-coded sequence. How do we do the pre-coding of a sequence? Right? As I said, that we do before modulation. So it is just XOR operation of the present data with the previous pre-coded sequence. I have considered previous pre-coded sequence reference bit as 0. Just I am doing XOR operation. I am getting this PN, right? Then the transmitted sequence denoted as what? A suffix n, right? So what is A suffix n? Will you be able to say A suffix n? So here it is written, right? A suffix m, right? A suffix. Yeah, A suffix m. What I am writing? -1 if Pn is 0. So this my Pm, what I written here, it is Pn only, right? If Pn is 0, I'll get it as A suffix m as -1. And when Pn is 1, I will be writing AM as 1, right? So based on that, I write here. So this is the pre-coded sequence. Now, if it is 0, what I write? -1 as the transmitted sequence. And if it is 1, I will be writing +1. I hope you'll be able to write by yourself now. Here 0, I am writing it as -1, and 1 +1, 1 +1, 0 -1, 0 -1, 0 -1, and here all it is 1 1 1 is there, so I am writing it +1. Then it is 0 -1, 1 +1, 1 +1, 0 -1. I hope is it clear? Writing the transmitted sequence means I represent 0 by negative pulse, 1 by positive pulse. That's all. Okay. So this is my transmitted sequence, that is AN. Then I need to find out the received sequence, that is BN. So BN is equal to what? AM plus AM minus 1. Na? BM. Yeah, here it is done, right? BM means there it is BN, right? Which is equal to what? AM plus AM minus 1. Right? So this is my transmitted sequence, right? This is if I can say this is AM, and this will be AM minus 1, right? So this plus this means -1 plus 1 will be 0, right? Then 1 minus 1, it will be 0. Then -1 plus 1, it will be 0. Then 1 plus 1, it will be 2. Then 1 minus 1, it will be 0, right? So -1 minus 1, it will be -2. Means we need to add up these two. This is the present and previous, right? So -1 plus 1, it will be 0, as I said. Then 1, right? Plus of -1, again it will be 1 minus 1 only, it is 0. right? Minus 1, so plus 1, it will be 0. Then 1 plus 1, it will be 2. Then 1 minus 1, it will be 0. Then minus 1, plus of minus 1 you have to write. So minus 1, it will be minus 2. Then minus 1, it will be minus 2. Then minus 1, plus 1, it will be 0. Then 1 plus 1, again it will be 2. Then 1 plus 1, right, it will be 2. Then 1 plus 1, it will be 2. Then 1 plus of minus 1, that is 1 minus 1 it is, right, it is 0. Then minus 1 plus 1, it will be 0. Again 1 plus 1, it will be 2. Then 1 plus of minus 1, that is nothing but what, 1 minus 1, it is 0, right? I hope this is clear. How do I write the received sequence? So
Yes,
just
sir.
present with the previous pulse, right? Present and previous. This is the present and the previous. Add these two and write what is the magnitude of that, right? Then how do I decode? At the receiver side, I need to decode, na? The decoded sequence. What is the decoded sequence formula? I think I wrote. See, dm will be equal to what? 1 by 2 bm plus 1. So this is the modulo 2 operation, right? So I found the value of bm, no? That is nothing but bn. So this is my bn, right? This by 2 plus 1. That is the modulo 2 operation, right? So 0 by 2, it is 0 plus 1, right? So 1 I will get. Similarly, here also, for this also I get 1. For this also I get 1. I hope it is clear. This is the value of bm. Just formula is here. The decoded sequence is 1 by 2 bm plus 1. This is the modulo 2 operation, what I said, right? Okay. So if bm is plus or minus 2, I will be taking the decoded sequence as 0. And if bm is 0, I will be taking decoded sequence as 1. Already I told this, right? Accordingly, you can write. So 0, I hope it is clear, no? 0, it will be 1, plus or minus 2 will be 2. So 0, I will be coding as 1. So 0, I will be coding as 1. 0, coding as 1. Plus or minus 2, I will be coding as 0, dm, right? So plus 2, 0. 0, I will be coding as 1. Minus 2, is there. So I will be decoding as 0, 0. For 0, I will be decoding as 1. Again, plus 2 is there, right? I will be decoding as 0, 0, 0. Right? For 0, I will be decoding it as 1. Right? Plus 2, 0. 0, I will be decoding as 1. So just compare these two. Will be similar. Right? This is the input data sequence and this is the decoded data sequence. They has to be same. Is it same?
Yes, sir.
Hello? Will you be, I think,
Yes.
I hope this is clear. Very, very simple it is. Okay, if I just say with those equations earlier, you may be feeling what is all these things, right? But if I consider this example and if I apply those formulas to find out what is the pre-coded sequence, what is the transmitted sequence, what is the received sequence, and what is the decoded sequence, is very easy. This is by considering binary, okay, binary signaling. Okay. If you have any doubts, please ask me right now. If you have any doubts in understanding.
Reference as one, sir.
If you take a reference bit as 1, then what happens? 1 XOR with 1 is 0. Exactly, you get opposite sequence. And ultimately, you do that by taking reference bit as 1 also. If you do, you will be able to achieve the same. You can do that as homework. Okay. Will you be able to, if you want to do it, you can, right now you can do it and say whether you will be able to getting the same result or not. Let's discuss that, or you can do it as a homework and we'll have a discussion in the next class if possible. Okay. Fine. Is it clear about this concept?
Yes, sir.
Yes, sir.
Yeah, other people, what about other people? Let me just come here.
Yes, sir.
Vandana is saying yes, sir. What about Shreyas?
Yes, sir.
Could understand, man. He'll be able to. Aishwarya, yes?
Yes, sir. Got it.
Got it, no? Okay. Gana? Gagana. So they are not speaking means they are not.
Sir, present.
Yeah,
Present, sir.
listening, na? Listening, you
Yes,
are
sir.
understanding what I'm saying.
Yes, sir.
Okay, okay. Fine. Teja,
Yes, sir.
you could understand, ma?
Yes, sir.
Okay. What about Sonali?
Yes, sir.
Sonali. Fine. Fine. Then let me go to the next one. Right. Uh, so this was the example, right? Mm. So now let me go to the M level PAM, right? This is by considering binary PAM. Okay. So let me go to the M level PAM. So just in M level PAM, I'm just extending from binary to M level, right? So what will be the changes? So again, the formula BM is equal to it is AM plus AM minus 1 only. And it has how many possible values? 2M minus 1, right? 2M minus 1 possible equally spaced levels will be there. So with that, I can write the amplitude levels, okay, as AM is equal to 2 PM minus of M minus 1. So the formula is also same here. CPM is equal to DM. Again, yeah, here it is not modulo 2 subtraction, right? It is modulo M subtraction. And this, as I said, modulo 2 addition and subtraction are similar only. But modulo M subtraction and addition are different. They differ. So this you have to check. So modulo M means if I consider the value of M as 4. Okay. So you should be able to apply modulo 4 subtraction. How do we do? And modulo 2, modulo 4 addition. How do we do? Okay. So will you be able to do that? Okay, so I have taken example of M equal to 4. Okay, let me see that. Okay, so the equation just will be generalizing it to mod M. Okay, nothing is different. There I wrote with respect to mod 2. Here I will be writing with respect to mod M. Okay, so wherever mod 2 is there, you replace that mod 2 by mod M. Okay, so this formula BM is equal to AM plus AM minus 1. And which is equal to what I wrote in the earlier case, PM plus PM minus 1 minus 1 I wrote. Here now it will be M minus 1. That's all. Okay, so if I take M as 4, so it will be 4 minus 1 is 3. So here in the earlier case I wrote it is minus 1 because the value of M is 2, so 2 minus 1 is 1 in that way. Okay. Yeah, this is the formula for pre-coded sequence. So here in the earlier case what I wrote 1 by 2 BM plus 1 was there, right? So here 1 is replaced by M minus 1. Means it depends on the value of M. It will be less than 1 of that. Right? And this is a decoded sequence. I wrote 1 by 2 BM plus M minus 1 it is. There in the earlier case, for binary case, it was plus 1. Now it is M minus 1. Means if I take M as 4, 4 minus 1 will be 3. Means 1 by 2 BM plus 3 will be there. Okay. So let me take the example, I think. You try by yourself this. Okay, note down this example. Let us consider the 4-level data sequence, okay, which is denoted as what? 0, 0, 1, 3, 1, 2, 0, 3, 3, 2, 0, 1, 0. Okay, this is my input data sequence, which has 4 levels. Okay, which has 4 levels. Let me write that level. Let me just say how do I write this level. This is a vertical line, what I wanted to represent. So if I consider this as 0, okay, then this is one level and this is another level, okay, and this side also another level and this is another level. Okay. So this will be what it is. I denote this with sorry. I denote this with minus 3, okay, minus 3, and this with the minus 1, okay. Means I am representing the amplitude level. -3, -1, and this will be +1. Okay, this will be +1, and this will be another. This one, as I said, this will be +3. Okay, +3. So vertical line. Okay, I could not write proper vertical line. You write that. So levels. No, I said level. 4 levels I have. Right? This is, I can consider a 0 level. Okay, and this is level 1. Okay, so level 0 I represent by means binary information. Means this is not binary. This 4 level information is there. No, 0, 1, 2, 3. So I represent 0 by -3, 1 by -1. Okay, then 2 by +1. Okay, 2 by +1 and 3 by +3. This is what I wanted to say. Okay, I hope it is clear. So that is what. See, I am considering 4 level data sequence. As I said, this is data sequence. Please note down this. So it is obtained by mapping 2 bits into 4 level symbols. Right? That is, I write 0, 0 as 0, 0, 1 as 1, 1, 0 as 2, then 1, 1 as 3. So these are the 3 different levels: 0, 1, 2, and 3. So we need to determine the pre-coded sequence, transmitted sequence, received sequence, and the decoded sequence. So same thing. So here, as I said, the value of m will be equal to 4. So how do I represent that amplitude, means transmitted signal amplitude level? Now, for 0, when I write 0, when the information bit is 0, 0, right? For that I am representing as 0. For that I am representing with -3 volts level. For 1 it is -1, for 2 it is +1, for 3 it is +3. So first I wrote here this input data sequence. So take this as small d suffix n only. So this is my input data sequence, right? And the pre-coded sequence is what? Same thing. I have taken initial bit as 0. So I am doing the XOR operation. Means modulo 2 subtraction I'm supposed to do. Right? So if I do, not it is modulo 2, here it is mod m. Modulo m. Means the value of m is here 4. Means modulo 4 subtraction I'm supposed to do. Right? If I do modulo 4 subtraction of these two, then I will be getting this sequence, this bit. Okay. I hope so you do this by yourself. I think you will understand. I am doing modulo 4 of these 2 bits, and then I will be getting this as my sequence. Okay. Then the transmitted sequence, how do I write? So this is what, for 0, I represent with -3. That is what I said, right? 0, -3, 0, -3. 1, I will be representing with -1. 2, I will be representing with +1. Right? 3, I will be representing with +3. 3 +3. Right? 1, -1, 2, 1, 1, -1, 1, -1, 3, 3, 2, 1, and 2, 1. I hope this is clear. No? That is why I wrote this. How do I represent this one? Okay, these levels. So you just try to understand this. How do you get this pre-coded sequence? By doing modulo 4 subtraction with the input data sequence and the previous data sequence, previous pre-coded sequence. Right? Do modulo 4 operation of these two and get this bit one. Then same thing, BM, that is the received sequence. No? In the received sequence, what I do? I add up these two, right? I add up these two. So if I add up these two, what? -3 plus -3 means it is -6. Then -3 plus -3, -6. Then -3 -1, it is -4. Then -1 plus 1, it is 0. Then 1 minus, right? Means here 1 plus 3. 1 plus 3 is 4. Then 3 plus 3, it is 6. Then 3 plus of -1 means it is nothing but 3 minus 1, it is 2. Then -1 plus 1, it will be 0. Then 1 plus of -1 means it is nothing but what? 1 minus 1, it is 0. Then -1 minus 1 means -1 plus of -1, it will be -2. Then -1 plus 3, right? It will be +2. Right? Then 3 minus, I think next is what? 3 plus 1, it will be 4. Then 1 plus 1, it will be 2. So I hope this received sequence, how we are getting is, I think, clear. And this is also clear, I think, transmitted sequence, how do we represent, right? Anyhow, this is given. Only challenge is here, how you get these things with the modulo 4 operation that you have to work out. Okay, once I know those things, then I will be able to decode the sequence, depending upon the magnitude of this. Right? That formula is there. What is that formula? So this is a formula. dm is equal to 1 by 2 bm plus m minus 1. That is a modem operation we do. Right. So based on that, I write this sequence, the decoded sequence, and this decoded sequence and the input data sequence should be same. So this.
Sir, can you explain pre-coded sequence once again, sir? For 1 and 3, how we'll get 2?
That is what I told you to do that modulo for operation by yourself. So these two should be equal. You try. I told in binary, na 1 XOR with 1, because I said in a modulo 2 operation, modulo 2 addition or subtraction are same, but in modulo 4, okay, subtraction and addition are different. So just apply that modulo 4 subtraction. Okay, take some time. Think it is time for you to think and do it. If not, you are getting, then I can definitely. Okay. Just have a try. Have a try for any of modulo 2 operation, you know, right? Mod 4 subtraction, how do you do? That is a crux of this. These things you should be able to know how you get. Yes, take time, take some time and do it. Okay.
Yes, sir.
That is why I said with modulo means with binary, if it is clear, then it's just a modulo 4 operation. So I think so far you have not come across this modulo 4 operation anywhere. Not tried, I think, right? Have you done in any, either in mathematics or in any other subject, modulo 4? Addition or subtraction? No. No, not done, na? I think that is why you're finding difficult. Modulo 4, just take example, okay? Like how you do for binary, in the same way, take this modulo 4, means maximum is 3, right? 0, 1, 2, 3 will get. So how do we code it? Means in case of binary, what do we do? 0 means XOR with 0, right? Modulo 2 addition or subtraction. How do we write the output of that? So first you write that clearly, then think about modulo 4. So this will be a simple task, but I left for you people to think about that. So if you are able to say now, I'm very happy to discuss. Anyone say about this? Then I think I love to end my session. Okay, if you have any, I think it is for just modified Leo binary. How do we do that? Okay, just you can have a look. I think so. In case of modified Leo binary, what I will be taking means x of n by 2w as minus 1. Right? When n is equal to 1, that is a negative pulse. Right? When n is equal to minus 1, I will be taking a positive pulse. That is what the meaning of this, what I have written here. Okay. For noise free, I will be writing this as am minus 2. Okay. So and other things are same. So the pre-coded sequence PM will be XOR of these two. Okay. And I think yeah, the decode sequence will be 1 by 2 BM modem operation. So the pre-coding of data to the transmitter makes it possible to detect the received data on the symbol by symbol basis without having to look back at previously detected symbols. Okay. So we say the error propagation is avoided in this case. Okay. So the symbol by symbol detection rule is not the optimum detection mechanism. Okay. For this partial response signals. But the thing is, it is very simple to implement. So that is what the advantage of that. Fine. So you are working out this model of 4 operation. Anybody?
So we can convert that three to binary and then 2 also to binary, and then we can do the XOR operations.
Try and tell me. Just simple task I've given. Just try from your side.
Yes, sir. We get it.
Get it? Oh, Pavan, Pranav. Is it Pranav?
Shreyas, sir.
Huh?
Shreyas, sir.
Shreyas. Uh-huh. Okay. Yeah, just you can share your understanding with your friend. You can just you tell from your side, man, how we have done it, so that
Sir,
others can
in
also.
1 is 0 1, sir, in binary,
Yeah,
and 3 is 1 1.
yeah,
So 0 XORed with 1, that first bit, sir. So it
yeah.
will be 1.
Okay. Then one
So
XR with 3.
with 1, it will be 0.
Ah,
So 1 0 is 2.
okay. That is why here it is denoted. Na? Here, see, it is mapped, right? 4 levels 0 0 to 0, 0 1 to 1, 1 0 to 2, and 1 1 to 3. So this you have to, means people have to understand, right?
Yes, sir.
Yes.
I think, got it, Akshata. Akshata was asking, I think, right?
No, sir. Mother is sir. I
Was it,
got it.
so could you catch what he said, your friend Shreyas?
Yes, sir.
So how do we represent, means how do we map that 0, 1, 2, 3 for this one? Based on that, we get this one sequence, okay?
Yes, sir.
So with this, let me close this session, okay? So let me see you on Monday. Fine? I hope everybody has written your USN in the chat box. Before you leave, please write your USN because showing 37 and here it is showing 27. Whoever has not written your USN, please write and sign off. Okay? Thank you.
Thank you, sir.